I'm a professor. So my name is Dave Reimann. I'm a professor at Albion College in Albion, Michigan. And this year I'm the visiting professor for public outreach at the National Museum of Mathematics in New York City. Today I want to talk a little bit about geometric patterns from positive integers. We'll get to that in just a moment. Um, so I just want to kind of point out a little bit where I'm located right now. I'm in Albion, Michigan, which is near the Great Lakes. And my home institution is Albion College, and I've been there for almost 30 years now. So currently, as I mentioned, I'm the visiting professor for public outreach at the National Museum of Math, MoMath, in New York City, and I'll be there until August of this year. So this is a view of New York City. So, as Seth mentioned earlier, one of the things I'm interested in is mathematical art, and I've created a number of different pieces. This piece, Pi, I put a link in that. Let's see, can I share your presentation? Um, I'm not sure that I can because it has a lot of images and it's very large, and I don't have it um, in a good location
It,
that I
it,
can easily share it. So.
it's recorded so they can see the presentation.
So it will be it is being recorded. So anyway, so I created this piece 20 some years ago, actually on Pi Day, so celebrating sort of a relationship between the circle and the digits of pi. Um, this was at a an art exhibition that I held that was held at the Museum of Math in the summer of 2023. Um, so I've also done this is countable infinity, and I'm sure that you can't see anything of the detail of this from your screen. Maybe if I zoom in on it a little bit, you can see that this is similar. It has the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, going on this lemniscate that defines this infinity symbol. So that's called countable infinity. Um, Here's one that's something I did this year called the square root of 2. And this is looking at 2 having this root structure that's a square, but along the diagonal is the digits of the square root of 2. Um, so as Seth mentioned earlier, I did cover art for Mathematics Magazine for about 5 years. This is one of the covers that I did. This is the number E represented using dots of various sizes for the digits. Starting at the center, we have 2, 7, 1, 8, 2, 8, and so on. And doing this in an exponential spiral, uh, creating this letter E. I also did this cover art that was 2017 represented as the sum of 3 cubes, 7 cubed plus 7 cubed plus 11 cubed. And if you add those up, you get 2017. And that was for the first issue of 2017. Um, so people have been interested in counting for a long, long time. Since before recorded history, people have been counting things. Um, and our notion of counting is really starts with this idea of abstracting um, the number of things with the with other entities. So for example, we might, in early counting, associate stones or pebbles or some kind of token like that for an animal, chicken, sheep, goat, whatever. And we can put these things in one-to-one correspondence. So we know that we have this, we may not know or have a number. Ancient peoples may not have had a specific number for the number of livestock that they had, but they could create a pile of stones that could be put into one-to-one correspondence. For every sheep, there was a pebble. And they knew that they had all their animals collected if they had, moved every stone from one pile to another pile. So this idea is kind of interesting, and we still use this notion today. We think about associating uh, things with other things. For example, in the United States, the history of the United States flag is such that there were originally 13 colonies, and those are represented by the stripes of the flag. And there are 50 current states in the US, and those are represented by this field of stars in this pattern. And this field of stars is interesting because it has um, alternating rows where the lengths of the rows different, or if you look at it from a column-based perspective, you have different numbers of stars in every other column. But regardless of how you count it, you still have 50 stars. The original US flag had 13 stars, one for each original colony, and these were placed in an arrangement where those stars were in a circular pattern. And unlike the previous version where it was a more rectangular shape, here we have a circular shape. Over time, new states were added to the United States and the flag changed, but these are kind of the bookends of those two patterns. So, so early civilization had simple counting, one to many. We can put things into one-to-one correspondence, states and stars, states and stripes, sheep and tokens, whatever. In some sense, counting works by giving the same number to different things. So stars and stripes or goats and whatever. And there's this fun quote that I like. It's by Henri Poincaré, French mathematician who lived about 150 years ago. Mathematics is the art of giving the same name to different things. So oftentimes when we think about mathematics, we're trying to classify something. We're trying to sort of throw away anything that is not what we want to talk about and focus just on some core essential idea. Um, and so we might think about a number as being uh, related to all the things that have that property of that particular number. So other flags have similar things, uh, similar star patterns as the United States in some ways. So let's look at some of those patterns. So um, so one common theme that we might have is that we have stars in a circle. Cabo Verde, the EU, Dominica, the presidential US presidential flag all have stars that are in a circular pattern. And this type of pattern is great because it doesn't matter how many stars we have, we can always make a circle that's larger and larger and larger to accommodate that number of stars. We also have stars that are along an arc or a line. So, for example, Comoros, we have four stars that are aligned vertically. Or Kosovo, there's an arc of stars. Uh, Same with Tajikistan and Venezuela. These countries all have an arc of stars that are corresponding to some number. And again, we can do that for any number of stars. There's also countries that have star patterns where the placement is not regular. So, for example, in Brazil, it's kind of related to, similar to, in fact, New Zealand and Alaska, corresponding to patterns of stars in the sky. Tuvalu, this is corresponding to islands in the sea, the islands that make up Tuvalu. So, one question that we can ask is, given a particular number of stars or other items, how can we place them in a way that looks good in some way? How can we think about a pattern that might be aesthetically pleasing? Now, some patterns, I would say, look good if they contain some symmetry. That is, maybe they can be translated as a group and land on others, or reflected about a point. There's some kind of reflection there, or they can be rotated in some way, or we might have a combination of all those things. So Placing one item is easy. So the flag of Ghana, very easy to place one star. Flag of Canada and Japan, uh, Vietnam, all very similar, right? We have one thing, we can just put it in the middle, looks great. If we have two things, these are going to be along a line. So different flags like Panama and Syria, they have two stars, and we can put those at any angle. They look, fairly balanced. Here in Panama's situation, they're equally spaced along this diagonal line from the top left to the bottom right. In Syria, they're placed kind of left to right of this center. Um, Placing three items, we can always place these in some kind of triangular pattern. So three different examples here. So one question that we could have is, if I have a triangular pattern like I see in these flags, how can I generalize this? If, for example, um, I wanted to expand this pattern that I see in the flag of Burundi, how could I do that? How could I extend that? Um, One way is we could just add another row of stars underneath that. So, for example, I could go from having just two rows, I could have a third row where I would have a star in this place, a star here, and a star here. Similarly, I could do that for the flag of St. Vincent and the Grenadines and place a diamond here, a diamond here, and a diamond here. So this sequence of numbers that we can arrive at in this way are called the triangular numbers. And these follow this sequence. So 1, 3, 6, 10, 15, 21, 28, 36, and so on. There's a great resource on the internet called the Online Encyclopedia of Integer Sequences, abbreviated OEIS. OEIS is a great resource if you're not aware of it. It has lots of information about different number sequences like the triangular numbers, and it gives each sequence an index number. This sequence is index A000217. And if you go to that page, you can see lots of information about this sequence, places where that sequence occurs in lots of different areas of mathematics, and why that sequence might be important to study in other contexts. So, but this is interesting, this sequence, because I can arrive at this if I just have one item. Well, that's all I have. If I have three items, it's because I had one item and then I added another row of two. I have six being the next sequence, and I can add three to the previous one and get six. And for the next one, it would be adding four to six to get 10. So um, this sequence, I can arrive at a couple different ways. I can arrive at taking the previous value, 10, and adding on the next value, which would be 5. That would give me the next item in the sequence, which is 15. I also have a closed form formula for this, n times n plus 1 over 2. And so that's a nice way of just saying, if I want to look at the nth number in this sequence, this is what that number would be. So placing four items. So if we're interested in placing four items, a common way of doing this is just putting them in a 2 by 2 grid. So here we can think about this as being a square pattern or perhaps a rectangular pattern. But let's think about it as a square pattern first. How can we generalize this square pattern? Well, one way to generalize this is to think about this as a sequence of numbers and to think about, okay, well, we had four, but the next largest square would be 9, a 3 by 3 grid. The next one would be a 4 by 4 grid, which would be 16, 5 by 5, 26, 6 by 6, and so on. But we can also arrive at this by adding a number to the previous number to get to the next number. So, for example, to go from 4 to 9, we added 5. To go from 9 to 16, we added 7. N squared is the sum of the first n odd whole numbers. So if I think about 16, it's really 1 plus 3 plus 5 plus 7. If I added 9 to that, I'm going to get 25. So a collection of n squared items can always be arranged in a square pattern that's n by n items on a side. So here's a visual that I created to help demonstrate that. So here I have 11 squared, and so I've used 11 different colors. Uh, so there's one of white, three of pink, six or five of blue, seven of brown, and so on to 21 of this purple color, giving me 11 squared. So another way that we could generalize square numbers is with rectangular numbers. So obviously, we've seen that any number of items can be placed in a single row or column. But if we want rectangles with two or more equal-sized rows and columns, what does that mean? It means that I have to have the same number of items in multiple rows or columns, and that's an indication that the number is not prime, that it's a composite number. So this is OEIS sequence A002808. So it is this set of numbers here. Unfortunately, well, or mysteriously, there's no closed form expression to generate the nth composite number or the nth prime number. That's still an open question. Is there such a formula? Can we discover such a formula? Um, so if a number is prime, it means that we can only form a 1 by p or a p by 1 rectangle of items. If we're placing 5 items, one possibility is to place them in a circular pattern like this flag of Hong Kong or Singapore. Another way is to form a 2 by 2 grid and put a star in the center. This is very common when you look at, say, dice. This pattern has a name called a quincux pattern. So a quincux pattern has 5 items that look like this. This pattern is kind of interesting. We can generalize this as well. We can think about this as a pattern where I have a centered square pattern. So I have one dot, and then I have four around that. I have a one, well, essentially 1 times 4, uh, or 4 times 1 items around that center point. And then the next one, I have 8 around that. The next one, I have 12 around that, and so on. So I'm adding 1 plus all the multiples of 4 to get to this pattern. So there's an entry in the OEIS for this. So as I mentioned, to get to this, we can just add these multiples of 4 to 1 to get the total number of items in that pattern. So that's those type of numbers are called centered square patterns and centered squared numbers, and they form this interesting geometric pattern. So, so as was mentioned earlier, I'm interested in mathematical art, and here's a picture from an exhibition that I had in the fall about a year ago, uh, 9 months ago, I guess. But here, this is each one of these small pictures that you see is a visualization of the numbers from 1 to 200. And I'm going to talk about those in the next few slides here. So in designing this or in working on this art project, I wanted to celebrate connections between numbers. So we've already seen that there's some numbers like triangular numbers and square numbers and centered squared numbers that have this connection with one another. Um, but what other patterns might be possible? I wanted all these to have a cohesive visual theme. So everything is white. The items are white, and there's a similar background. I wanted to show only those motifs, only those little individual items. Each one of those was going to be the same size and shape, but I'm going to allow for things to be rotated and translated in some way. Ideally, each design exhibits or illustrates some aspect of that number. I also wanted them to have a compact structure that was reasonable to count, whatever reasonable is. Uh, Certainly, as you get larger and larger, things become harder and harder to count. Um, but um, but anyway, I also wanted these to be thought about as a two-dimensional image rather than some 3D image with some items that were hidden. So I didn't want to rely on the viewer's sort of sense of three-dimensional structure to infer that there were some items that were there. So, so as I'm looking at this, as we look through some of these slides, I want you to think about what is it about this pattern that you notice, or what about this pattern do you wonder about? So here we go. So here's some examples. So here's four examples, and these are sort of representative of the number themselves in some way. So for example, 12 has an interesting connection. A lot of cultures use 12 in a special way. In the US, there's numbers for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But then after that, we have this pattern 13, 14, 15, and so on. But 1 through 12 are kind of uh, their own thing. So one thing that you might know is that in your hand there are three bones in each finger, and so if you want to count, you can count one. You can count something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So on one hand, you can count from 1 to 12 using this way. So so this image here is kind of thinking about each one of these items representing one of the bones in your finger, uh, and your hand held out in kind of this way. And then here for 20, here I have 20 pentagons that are arranged in this X pattern here, uh, that are representative of the Roman numeral XX, which is 20. Uh, and then here is 69. So here, something that looks like a 6 and something that looks like a 9. And because they have the same number of things, you need a little one extra piece to join them together. Uh, 94 is the atomic number of plutonium. So plutonium has 94 protons, and this is the symbol for things roughly of things that are radioactive. So um, so sometimes these things, these numbers, these patterns that I've created associated with numbers are things uh, that we think about when we think about those particular numbers. Um, in some cases, we have squares. So, for example, 3 by 3, that's 9, and 10 by 10, that's 100. These are probably not too surprising, so I won't dwell on those too much. We'll talk a little bit about my process for creating these. Originally, I would start with a collection of pennies or a collection of little glass beads. So I have a, let's see, I have a jar of little glass beads that I would pull out, or coins. But you could do this with any kind of thing that you have. You might find stones or pebbles or seeds or something like that. You could create your own patterns um, as needed. So 53 is a prime number. So these were different patterns that I was considering, and I ultimately ended up settling on the pattern that you see here. And if you look a little closer, you can see that's the pattern that is here. So it's 53 is 4 times 13 plus 1. So each one of these, well, there's the 1 that's here, and then this has like a 4 by 4 square with three of the items missing. So that's 13. So um, so it turns out that anytime we have a prime of the form 4k plus 1, we can always write that as a sum of two squares. So, for example, um, is my screen being displayed now for people? I'm seeing
Yeah,
I'm seeing a different screen.
we can see the screen with the
Okay.
prime of the form.
Okay. Great. Just double checking. Okay, so anyway, if I look at 13, it's a prime number, but it's of the form 4k plus 1. It's 4 times 3 plus 1. So I can arrange it as a sum of two squares. And in this case, it's 3 squared plus 2 squared. 41 is also prime. It's of the form 4k plus 1. It's one more than a multiple of 4, 4 times 10 plus 1. In this case, I can represent it as 5 times 5 plus 4 times 4. Similarly with 97 and 109. Um, Another interesting theorem that I learned way back when I was in college taking a course in number theory is that every positive integer can be expressed as a sum of squares using at most four squares. This was another cover art that I did for Mathematics Magazine. This was for volume one, number 5, and it turned out if you were going to express 91 as a sum of four squares, there were 5 ways to do that. So there was a nice kind of coincidence between 91 and 5 going on. And so I arranged these in this way, and that was the cover for Mathematics Magazine in December 2018. So you can also form these rhombic patterns like this. It turns out you can think about this as a square that has just been skewed. So it's kind of a stretched out square. So it forms this diamond shape, and you can arrange those in some fun ways like you see here. We've talked about triangular numbers, so 45, 105, 136, 171. These are all triangular numbers, and so we can arrange them in this nice triangular shape. Related to this, we have something called a centered triangular number, and these are a more complicated form, but they still form a nice triangular shape. The grid pattern is slightly different than what you saw with the triangular numbers, but as I mentioned, this is still a fun pattern to look out. So so a couple questions that I'm seeing here. How did I choose the best pattern from all the possibilities? Uh, in some ways, I was looking at um, how this fit into the sequence of things. So I didn't want to have too many triangles in a row or too many squares in a row. Um, I was looking at, um, certain options, and I've done a lot of these. And so I also wanted to have, some variety, but also, um, okay, so I'm somewhat lazy and I didn't want to do a lot of work, but I still wanted to have something that looked interesting. So I kind of quit when I found something that was interesting, but that was that. Okay, and someone is asking me to slow down a little bit. Okay, I'll try and slow down a little bit. I just get super excited sometimes when I'm talking, and so I'm sorry if I'm fast, but it's being recorded, right? And people can watch the recording if they want. So, um, okay. So another type of pattern that's interesting is the centered hexagonal numbers. So these centered hexagonal numbers are common uh, if you have something like pencils, or I'm looking for something that I can just grab quickly. Whoops. Well, my bundle of pencils is on the other side of the room, and it's not very easy to get. I'll make do with the pencils that I have. It turns out if you have a honeycomb or a bundle of sticks or something that are all the same size, it naturally forms this hexagonal type pattern here. Um, if that pattern is symmetric all around, we can get some patterns that look like this. 19, 61, 91 are all patterns of this form. Um, and you might see these patterns in interesting places. It's very common in the United States to see a drain that has 19 holes arranged in this pattern. And sometimes you might see other other objects that are arranged in this way. Um, so centered hexagonal numbers, they're of this form. They're 1, 7, 19, 37, 61, 91, and so on. There's also another fun pattern called star numbers, and these include the numbers 37, 73, 181. 121 is also one of these numbers, but um, here you can see that depending on the pattern, I chose to use here little individual stars. Here they're hexagons. Here they're just circles, um, just to add a little bit of variety to these patterns to give them some distinction. Um, so as I mentioned, the star patterns uh, are of the form 6n times n minus 1 plus 1. Powers of integers are also interesting. So here we have 3 cubed. So I can think about, well, I have 3. If I have 3 of those together, I'm going to make a larger triangle. And if I have 3 of these triangles of this size, then I get this larger triangle. And if I have 3 of these, then I'm going to get something that looks like this pattern here. So this is a kind of fun thing to do with powers of numbers. So here's 5 cubed. So you can form these in sort of a pentagonal flower pattern. Another thing that I've done here is use this idea of composition, pattern composition. So oftentimes we think about function composition. I might have one function that I feed the output of that function as the input into another function. Here we can see that in kind of a visual way. I've taken this square here, and rather than using just the square, I've broken it up into 4 quarter circle pieces and used that as the basis of this pattern here. And so rather than just having one square here, each square has become 4 quarter circles. And so what was 13 has become 52. A couple more of those. So here's a ring of 5 things, but those 5 things are these centered hexagonal numbers. And sometimes it's fun that you can create um, in this kind of negative space here, you can see that there's a star. And so it's kind of fun to play around with both the positive space where there's the items and the negative space where the items are missing. And for 195, here I have a triangular pattern where each one of the items in the triangular pattern is this kind of star pattern that we see here. So this one is kind of interesting. Um, if you know Pascal's triangle, I'll start just by mentioning something about Pascal's triangle. Start with a 1 here, and then put a row of 1s underneath that, so 1, 1. And then you have 1 on the left, and then you add the 2 above, and you get 2. And then you put a 1 at the end. And you repeat that. Start with a 1, add the 2 above, 2 and 1, you get 3, 2 and 1, you get 3, and put a 1 to finish that off. Each row has an increasing number of items, and in this row that has a 7 in this location, So I can think about this as row 0 and row 7. This row 7 here um, has the numbers 1, 7, 2, 1, 3, 5, 3, 5, and so on. Um, Here in this, I've color coded all of the odd numbers in this gray. Those numbers are black with a gray background, and the even numbers are in red with a white background. Um, when I have one less than a power of two for the row, every one of those is going to be odd, like we see here. Also, what's interesting is that every row corresponding to a prime number, all of these interior numbers are multiples of that prime number. So, for example, in this row, these numbers here are multiples of 7. These these items here are multiples of 5. These are multiples of 3. If I were to go up and look at the row that had the 11th row, all of those interior numbers would be multiples of 11. Well, you can use this uh, in an interesting way to create a pattern like what we see here. So if I add up all the numbers in this row, it's going to be it's going to be 2 to the 7th power. That's 128. So if I subtract 1, leave out this one here, I'll get 127. If I place this one here in the center, then I have 7, 21, 35, 35, 21, and 7 left over. I can build a shape that looks like what you see here, 1, 3, 5, 5, 3, 1. And if I have 7 of those, that's going to give me the numbers that you see here. So this pattern here corresponds to the numbers that you see here. And again, because these are multiples of 7, I can create something that has this sevenfold rotational symmetry to it, adding this 1 here at the center, and that gives me 127 items. So as I mentioned, I did this collection for all the integers from 1 to 200. I have some extra ones, and this is an ongoing project for me. So uh, luckily, I can do this forever because there's always one more integer for me to create a pattern for. Um, this is my pattern for 2025. So a fun thing about the number 2025 is that it is 45 squared. Um, so it's a 9 by 9 pattern with each one of the blocks being a 5 by 5 pattern. So it's kind of like a squared square. So you have 9 squared and you have 5 squared uh, working together. This is 10,000. So I have a 10 by 10 grid. Each one of those subblocks is 10 by 10. Part of my goal here is to help visualize what 10,000 things look like. So here, the town that I live in Michigan, has just under 10,000 people. And so here I can think about this as being representative of 10,000 people. Um, this little this little bin here has about 10,000 little green beads in it. It's another way of visualizing 10,000 things. So, the last number I want to talk about is the number 143. So, it turns out that today is the 143rd day of the year. And in the US, there's a famous television show, Mr. Rogers' Neighborhood, that was uh, broadcast in the 1970s and 80s, somewhere a while ago. At any rate, the person, Mr. Rogers, Fred Rogers, um, was fascinated with the number 143, he said that the number 143 means I love you. It takes one letter to say I, four letters to say love, and three letters to say you. 143, I love you. Isn't that wonderful? And the number 143 made different cameos on his show at different points. So here is the number 143 in my series. So this has 143 hearts. So so this is me sharing my love of mathematics with the rest of the world. And and so 143 hearts to all of you. So this is kind of uh, an interesting exploration. So these are things that people can do on their own. For example, you can you can find number patterns in everyday objects. For example, if you have a lid that has holes in it, you can look at, well, how many holes is in that pattern? And is that pattern interesting? Um, or you could create your own pattern. Think about your age um, or a number that has some kind of special meaning for you. Might be your zip code or street address or other special number. You could create a pattern of items that would represent that number in some fun ways. You can look for your number in a sequence that's on the OAIS. OAIS has a search. You can just put in a number and it will return all the sequences that contain that number. So, um, so hopefully that's fun things that you can do. Um, so I just want to thank you, and I'll leave you with this quote that a mathematician, like a painter or poet, is a maker of patterns, and that's from G.H. Hardy. So, and be happy to answer any questions that you might have.
Okay. Thank you, Prof. Reimann. Um, that was a wonderful talk. I enjoyed it so much.
Thank you.
Um, so, yeah, are there any questions from the audience? Maybe I can start. So, I think most of the people here, okay, because I'm the host, I'll give Rebecca the chance to go first. Rebecca, you
Okay.
can unmute yourself and talk.
Okay. Thank you very much, David, for your presentation. But I asked the question, but I didn't get the answer. That's why I'm trying to ask it again. I said, do you use a particular software for making all these beautiful patterns? We want
Oh,
to know.
yes. So the software that I use is software called Processing, and it's available on processing.org. It is a Java-based language. There's also one that is JavaScript-based that you can use, p5.js. Um, it's a very nice programming language in for this kind of work because the output is designed to be a visual image. So the graphics are very central to that language.
Okay, that's nice.
So if you're looking at learning how to program, um, it's a great language to use as a first language.
Mm.
Um, there are other nice languages to use as well, but there's some like if you're very young, you might want to use a language like Scratch, but it doesn't have the image output capabilities that a language like processing does.
Okay, that's nice. Yeah, and David put the uh, link in the chat, so you can check the chat if you're looking for the link.
Yeah,
Okay.
so I put yeah processing.org and P5JS in the chat there. So it looks like so Bruce says it looks like my house is full of things I can make patterns with. Can you tell us some of the other things that you play with when I'm creating art? Um, a lot of times I'm just just sketching things on a piece of paper. So I have some, just some, I have a ruler and just a piece, lots of paper and pens and pencils. In fact, I have I have a lot of rulers. Sometimes I need more than one ruler for something that I'm working on. Um, sometimes sometimes I use Lego. So, for example, uh, let's see. I have Legos here, so sometimes I use Legos to create interesting patterns, like what you see here.
Oh, nice.
So, um, and then let's see. I'll try and use that to show something else that I've done just on another little thing with Lego. Um, so these are some in this upper part here, just little tiny bricks that you can use to make patterns like that. Um, let's see, what else? I have, yeah, I don't know. I have lots of stuff here. Uh, but those are the things that are easily within my reach. But sometimes I draw inspiration from lots of things. So having things like geometric shapes. So I showed these before the talk, these little platonic solids, the dodecahedron and the icosahedron. Sometimes I think about these when I'm creating something that's three-dimensional. Um, so for example, something that looks like this uh, is is made from 60 squares that are connected at their corners. So you can see that each square has four holes in it, and they're connected in this pattern that looks like this. And this is uh, in some ways related to the dodecahedron. Uh, some of these openings have um, five squares around them, and there are 12 of those, just like you have in the dodecahedron. It's also similar to the icosahedron, which has 20 triangular faces. And you can look, there's on this, there are some 20 triangles that are on the face of this object as well.
Mhm.
So those are a few things that I have handy,
Great.
just looking around to see if I have other things.
Yeah, that's nice. There's another question in the chat. Uh,
Oh, if you could create another wall-sized installation art, would you do another set of numbers 1 to 200 or something completely different? Um, you know, I've been working on this project from well, I have the 1 to 200, but I also have some other numbers associated with those, like the 2025 and so on. But I'm I just realized that I have a paper that I can share. Um, so I gave a similar talk about this last year, and so people can find the information on this link here. Um, so you can download. So on this page, you can see that there's a download the PDF. So you can see the images that I've created for the numbers from 1 to 200, but also there's a supplement that's linked on that page. That supplement has information about the integer sequences and some common integer sequences that you have. So I think if I were to do this, maybe sometime in the future I would create 1 to 100, but using rather than computer generated things, perhaps actually physical objects. So looking at um, maybe a collection of items that would relate to some overall theme in some way. Maybe it would be plant seeds um, or things of that nature. Um, so um, so yes, so if people are interested in contacting me,
Mhm.
my email I just put in the chat. Um, so so there's that. So yeah, I think part of my goal with this project is to get people to think about numbers and get people to visualize what it looks like to see some number of items,
Mm.
also to make them in a pleasing geometric way that is somewhat easy to count, but also uh, to think about how we can use this to say, you know, what would be the next item if I want to start with this pattern, what would be the next number in that sequence? So, why only positive integers? I like to be positive. There's too much negativity in the world. I just want to focus on being positive.
Right. Also, I mean, so most of the viewers here are teachers.
Uh-huh.
Do you know if there are some resources, to help the students get a feel of positive numbers? Do you know
Hmm.
how teachers can?
Well, I think from the standpoint of telling a student, okay, bring in 100 of something,
Mhm.
whether it's seeds or pebbles or something like that, and just to ask them to say, what kind of interesting pattern can you create with, 10 things or 20 things? And think about, showing um, maybe showing flags which have some number of items on them as a way of maybe inspiring them in some way. But, perhaps it's a way to lead them to think about, well, um, I can only make a rectangle when I have a composite number.
Mm.
Um, One of the things that I was trying to do when for a different art project, I was trying to come up with a pattern that I needed to arrange 26 things. And so I was looking for what is a nice way of representing 26 things. And I just couldn't use, well, a 2 by 13 rectangle just didn't seem to look nice. I wanted something more compact.
Mhm.
And so using what you see in this series for 26 is what I came up with for that artwork. So that artwork, I had 26 different things that I wanted to represent, and so that's what I chose to do. So
Mm.
let's see. So I did share my um,
Your email.
so let's see. So let me just say here. So if you go to my website, on my website, there are links at the bottom of that page to different social media sites: Mastodon, Facebook, LinkedIn, Blue Sky, Instagram. It does have an email, but probably the best email to reach me at is this is my college email, uh, which is uh, I put in that. Oh, I guess I didn't. I guess I'm sending these. Someone messaged me, and
Okay.
I'm responding to them rather than to everybody.
Yeah.
So,
Okay.
uh, so anyway, let me try this again. So that's my
Your website.
that's my website where you can get my social media contact information, and then my email. The best email, rather than what's on that website, is my one that's at Albion College, which is dreimann@albion.edu.
Okay. Um, Okay, yeah. Also, as a reminder, please fill the forms that Emmanuel posted is the attendance form just to get a count of how many people joined today. Okay.
So I'm trying to fill, but it says I've already filled it.
Okay. That's fine. Maybe then we will capture it's captured you already, so that's fine. I had another question. So,
Sure.
when you were showing the patterns,
Mhm.
there was also a comment in the chat about fractals because we saw some
Oh
patterns
yeah.
that looked like fractals. So,
Yeah. Let me.
so the question is, like these patterns you form, do they have some deep? Are they connected to other mathematical um, objects? Yeah, this one.
So, so for example, this pattern with triangles is interesting. So 81 is 3 to the fourth power. And the pattern that you see of where these white triangles are placed actually is the same as what you see in Pascal's triangle here. And the fractal that's related to this is called Sierpinski's triangle.
Yeah.
And and so there are some really kind of fun connections between this pattern that you can form with triangles, 3 to the nth power, and Pascal's triangle, like you see here.
Mhm.
So, um,
Yeah.
so that's what I'm thinking off the top of my head.
Yeah. It looked interesting. I saw the pattern from the Pascal's triangle too.
Yeah. And this is a fun, it's a fun thing that you can create using, um, lots of different objects. And as a, you can also do this in a three-dimensional sense. You can use something called Sierpinski's triangle. And let's see, I have one made out of playing cards up here.
Oh yeah. I see.
So, uh, so anyway,
Okay. You have quite a collection in your room.
can you repeat that question?
I just said you have quite a collection in your room.
Yeah, I have a lot of stuff in my my office here. So, uh,
Are there any questions? Carl? Carl is here, maybe.
So, thank you very much,
you're welcome.
Professor Reimann. We are very grateful for your time, and thank you very much, Seth. And I also want to thank Dr. Bailey. I think I can also see Dr. Isaac Okulu from Bowling Green University in the US also joined. We are very grateful for your presence. I just want to put across for the Google Forms that you are filling, you could see there are some of the questions that asks whether you'll be interested in reviewing a digital textbook that is in the process for grade 7. Actually, it's a project that Guidance has started, and that was a week ago. There was conference at the University of Ghana, Legon, and then one of our partners spoke on that. And another group of partners from Kenya called Innodems. They've started something like that, and then we are collaborating with them to have a similar project for Ghana. And it's an opportunity for teachers to own this kind of projects. You'll be acknowledged accordingly for your reviews. But then if you want to go deeper into the authorship, then there are other things that you need to fulfill. One of the major things is to have some idea about GitHub. Don't worry. If only you are interested, you'll be taken through the training if you are interested, and then you go through the authorship. We will start from grade 7 to grade 12. That's the JHS 1 to the senior high school level. So if you are interested, please kindly indicate that portion in the Google Forms. that has been posted on the chat. If you are not able to fill the form, don't worry. I'll get in touch with you on the WhatsApp group page to give you a bit more details on how to go about it. Thank you very much. This is just what I want to put across. Thank you. Set. Yeah.
I'm muted, yeah. So yeah, we are getting towards the end of the presentation. Are there any final questions for Prof. Reimann? Yeah, if the Justice, you have your hand up. You can unmute.
Yeah, the pattern that is being displayed right now, that we got from the Pascal triangle, I'm very interested in that one. But I'm trying to study the pattern to see the connection between the figures that are being displayed here. With the first one, I got it. I realized that we have three bigger triangles. If I look at the triangles for the first one, I can see three bigger triangles. And each of the big triangles, you can also see three triangles in each of them. And it helps me to appreciate the figure 3 raised to the power 3. But when you come to the second one, the 81, which is 3 raised to the power 4, I'm trying to identify the 4 in the pattern. I'm not getting it. Can you please help me?
So one way to think about that is that so when I have one triangle by itself, that's 3 to the 0 power.
Okay.
And in the negative space, I don't have any triangles. But if I have 3 to the first power, I have one triangle that's in that negative space, and it's of this size. If I have 3 squared, I have triangles in the negative space of 2 different sizes. And if I have 3 cubed, I have triangles of 3 different sizes in that negative space. Okay. And over here, then I have 4 of that.
1, 2, 3.
So 1, 2, 3, 4.
Could you also say, like, you take the first picture and you repeat 3 times and then
so this pattern here that you see here is also what you see up here. I have 3 of those that need to go together to make this pattern. And similarly here, the 5 cubed, I have 5 different sizes of pentagons. So I have 1, 2, 3 different pentagons that are in this negative space, corresponding to 5 to the third. So I have a pentagon here of this size, and then I have a pentagon of this size, and I have a pentagon of this size. Is that helpful?
Yes, please.
Thank you.
Okay. So the 4 is the off triangle, the negative triangles in the paper.
Yeah.
Nice. Okay. That was a good question. Any more questions? Okay, if there are no more questions, then we will end the meeting now. So thank you once again, Prof. Reimann, for your time. And
thank you. Thank you everyone for coming.
Yeah, I think we had a good time tonight. So
yeah.
And thank you.
And if people, I would encourage, if anyone has any questions about anything, you can always consult that paper, but if you have more questions, feel free to reach out to me at on social media or in this way. If you choose to do some exercise like this in a classroom, I'd love to see work of students, and love to have you share that with me. And I just hope that you can find this useful in some way.
Okay, that's nice. Yeah, thank you everyone. Thank you, Dr. Bailey, and thank you everyone for joining. It was nice to have you. So have a good night to you all.
Thank you. Bye.
Bye.